In this R code tutorial, we'll use our Tidy Models tools to perform k-fold cross-validation. Throughout, our goal will be to build a linear regression model of the height and feet of a black cherry tree by its diameter in inches. Upon building this model, we'll evaluate it using k-fold cross-validation. Let's do some setup. First, we'll load the Tidyverse and Tidy Models packages that we need for our analysis. Second, we'll load the data that we need, and this tree's data is just built into R. And then we'll plot our relationship of interest before doing any modeling. Now, from this plot, notice that height is weakly and linearly related to diameter, and there's a positive association. Mainly, the bigger the diameter of a tree, the taller it tends to be. So as a review, let's build this model using our Tidy Models tools. In Tidy Models, our first step is to specify the model or algorithm that we want to use. And I'll store this as lm_spec. So in this particular analysis, we want to build a linear regression model in the regression mode, meaning our outcome variable height is quantitative, and we want to build this regression model using the lm function or engine within R. Now that we've specified our algorithm, we can use it to estimate our particular relationship of interest. And we'll store this as tree model. So we'll take our algorithm and use it to fit the relationship of height versus diameter using our tree's data. We can now use our model to do things like make predictions. So we can predict the height of a new tree by its diameter. But we're going to focus in this video on evaluating the quality of these estimates. And we'll do so using tenfold cross-validation. Now recall that for tenfold cross-validation, we randomly split our data into tenfolds. And then we build the model 10 separate times, leaving one test fold out each time. And then we evaluate each model on the test fold we left out using the MAE and R squared. So to implement this in R, first, we focus on this word randomly split. And because this splitting and modeling process is random, we want to set the random number generating seed in order to get reproducible results. And here I'll just use the positive integer 253 as a demo. Next, we want to build our model 10 times. Every time we run a model or build a model on a certain set of folds, or 9 folds, we're going to use the same algorithm that we used to build our kind of singular model above. That is, we'll use lm_spec. Now, when we had built just one model using our entire data set, the function that we used was called fit. But because we're going to build our model 10 times on 10 different kind of combinations of folds or resamples, we'll use fit resamples. Resamples you can think of as another word for folds. So we want to fit our folds. And just as when we fit our model using all of our data, the first argument that we need to specify is the relationship of interest. Mainly, each time through our model, in our k-fold cross-validation algorithm, we're going to model the relationship of height by diameter. Now, the second argument, when we build this model using one data set, we specify what data we're going to use to fit this relationship. So here in k-fold cross-validation or tenfold cross-validation, we don't use the entire tree's data set. Instead, we use different combinations of these 10 folds. So in this step, we need to specify what these folds or resamples are. The function that we'll use here is called vfold, CV, And it takes two arguments. First, we specify our original data from which we'll pick these 10 folds, and then how many folds we want to pick. So V here just means K. So again, in this step, we're just defining what are the 10 folds. We want 10 of them, and we're going to randomly select them from the tree's data using this function vfoldCV. And finally, each time that we build this model of height by diameter for different combinations of these resamples, we're going to evaluate each model on the remaining test fold using MAE and R squared. So in our last argument here, that's what we specify. We have certain metrics that we want to use to evaluate our models. So the metrics argument, we can set our metrics using metric set, and there are multiple metrics that we might use. We might just use MAE, but here we'll use both MAE and R squared just as a demonstration. So I can run this chunk, and in summary, what we're doing is setting the random number seed because cross-validation does some random sampling, and we want that to be reproducible. And then each time through the cross-validation algorithm, we're going to use our linear regression algorithm to fit our resamples. Specifically, we'll fit or estimate the relationship of height by diameter using our 10 folds, where one fold is left out, and we'll evaluate that model using our MAE and R squared metrics. All right, so tree model CV includes a bunch of information. Let's first just pull out our final results of that cross-validation process. So we'll take our tree model CV, and to pull out our final cross-validated metrics, we can use the function called collect metrics. When I run this code, notice that I get a cross-validated estimate of the mean absolute error as well as R squared. So to interpret these, in this particular setting where our predictions are predictions of height of a tree in feet, this cross-validated metric means that we expect our predictions for new trees to be off by roughly 4.4 feet. Similarly, for new trees, we expect that our model explains roughly 58% of the variability in height from tree to tree. Now these are the final metrics, but remember to get these metrics, we had to do in the 10-fold procedure, we built 10 separate models and evaluated each on the test fold that we left out. So to learn more about these details and what happened exactly in each of those folds or each of those 10 models, we can get fold by fold results. To this end, we take tree model CV, and we want to unnest the information. Unnest or take out the information that built these metrics shown here. So we want to unnest these metrics. Oops, and maybe I need unnest.metrics. One more time. There we go. So I take my cross-validated outcomes and I unnest the metrics. And notice then that I get information of what happened for each test fold. So the first row tells me what was the specific MAE when we left out fold 1 and tested fold 1. Similarly, what was the R squared when we left out fold 1 for testing. So if I'm interested in just looking at the MAEs or just the R squareds, for example, I'll do that here as a demonstration. I can just filter out the particular metric I'm interested in is MAE, for example. All right, so this is a little bit easier to understand and look at. So notice I have 10 rows here. Each row corresponds to a different fold, or test fold specifically, and what was the MAE for that fold. So we can skim these and notice that when we left out fold 1 and built the model using folds 2 through 10, the typical prediction error for the fold 1 that we left out was 1.7 feet, and so on. And so we see that these prediction errors vary from fold to fold. The prediction errors were the worst for fold 3, and they were the best for fold 1.